Imagine holding a grain of sand, that tiny speck between your fingers. Now consider that everything you see, everything you know, from the towering mountains to the swirling galaxies, is composed of something even smaller, something more fundamental. But what is that something? What is the very essence of reality? For centuries, humanity has grappled with this cosmic riddle, this yearning to understand the universe at its most basic level. We've looked to the stars, peered into the atom, and scribbled countless equations in a relentless pursuit of the ultimate answer. It's a quest that transcends mere scientific curiosity. It's a deep-seated human desire to know our place in the cosmos, to unravel the secrets of existence itself. Think of it as the ultimate detective story, a cosmic whodunit where the clues are scattered across the universe and the suspects are the very forces that govern reality. This isn't just about particles and forces. It's about the very fabric of space and time. It's about understanding how something so complex and diverse could arise from something so simple and elegant. Perhaps it's like a grand symphony where countless instruments play in harmony, all guided by a single overarching score. Or maybe it's more like a colossal jigsaw puzzle where each piece, no matter how small, is essential to completing the grand picture. This search for a single theory, a master equation that can explain it all, is arguably the most ambitious undertaking in the history of science. It's a journey into the unknown, a voyage to the very heart of existence. And while the path may be long and arduous, the potential reward is nothing less than unlocking the secrets of the universe, of finally understanding what it all means. But why is this quest so important? What difference does it make if we can explain everything with a single equation? Well, imagine having the blueprint to reality itself. Imagine being able to predict the behavior of everything from the smallest atom to the largest galaxy. Imagine the technological breakthroughs, the scientific revolutions, the philosophical insights that could arise from such profound knowledge. This isn't just about abstract equations and esoteric concepts. It's about transforming our understanding of the world, of our place in the universe, and of our potential as a species. It's about deciphering the blueprint of reality, a journey that will undoubtedly challenge our assumptions, push the boundaries of human knowledge, and perhaps, ultimately, reveal the face of creation itself. The journey promises to be filled with twists and turns, with unexpected discoveries and mind-bending concepts. But one thing is certain. The quest to understand the universe is a journey worth taking, a journey that will lead us to the very heart of existence. But this thirst for knowledge, this relentless pursuit of a singular truth is not a modern invention. It's a narrative etched into the very foundations of human thought, a story that begins long before the advent of particle accelerators and supercomputers. Imagine, if you will, a world devoid of our sophisticated instruments, a time when the night sky was not a canvas for satellites, but a source of profound wonder and untamed mystery. Picture ancient Greek philosophers gazing up at the same stars we see today, not with telescopes, but with minds ablaze with curiosity. These were the intellectual pioneers, the first to dare to ask, what are the fundamental building blocks of existence? Men like Thales of Miletus, a pre-Socratic philosopher living around 624 to 546 before Common Era, who believed that water was the primordial substance from which everything else originated. Water, the life-giver, the ubiquitous element that seemed to be everywhere, transforming from solid to liquid to gas. It was a bold assertion, an attempt to distill the overwhelming complexity of the world down to a single unifying principle. Then there was Anaximander, born around 610 before Common Era, who proposed the apeiron, an undefined, unlimited substance from which all things emerge and to which they eventually return. A concept so abstract, so encompassing, that it seems to foreshadow the modern physicist's search for a field that permeates all of space and time. And let's not forget Democritus, born around 460 before Common Era, the father of atomic theory, who envisioned an universe composed of indivisible particles, atoms swirling in a void. An idea so prescient, it laid the groundwork for centuries of scientific inquiry. These early thinkers weren't just making guesses. They were laying the foundation for a way of thinking, a method of questioning that would ultimately lead to the scientific revolution. They understood that beneath the surface of everyday experience lay a deeper order, a hidden logic waiting to be discovered. But the quest for unification wasn't confined to the realm of philosophy. As civilizations rose and fell, so too did our understanding of the cosmos. Early astronomers, meticulously charting the movements of the stars and planets, sought to unravel the celestial dance, to find the mathematical harmonies that governed the heavens. Consider Ptolemy, the Alexandrian astronomer living around 100 to 170 Common Era, whose geocentric model of the universe with Earth at its center dominated scientific thought for over 1,400 years. While ultimately incorrect, Ptolemy's model was a testament to the human desire to impose order on the apparent chaos of the cosmos, to create a framework that could explain and predict the movements of celestial bodies. Or think of the incredible astronomical observatories built by ancient cultures, from Stonehenge in England to the Mayan pyramids in Central America. These structures weren't just monuments. They were sophisticated tools for tracking the cycles of the sun, moon, and stars, allowing these civilizations to develop calendars, predict eclipses, and understand their place in the cosmic order. The Babylonians, masters of mathematics and astronomy, meticulously recorded celestial events for centuries, searching for patterns and correlations. Their observations laid the groundwork for later Greek astronomers and mathematicians, providing a vast data set for future generations to build upon. These weren't just isolated observations, they were steps towards uncovering the deep interconnectedness of the universe, a quest for understanding that would continue to evolve and shape our destiny, a quest fueled by an insatiable curiosity, a burning desire to know. And who knows what future discoveries await us as we continue to follow in the footsteps of these early pioneers. But even with these monumental achievements, a complete, unified picture remained elusive. The celestial sphere, so meticulously mapped, still seemed disconnected from the everyday world of earthly objects. Could there be a single set of laws, a universal principle that governed both the heavens above and the ground beneath our feet? The answer, it turned out, was closer than anyone could have imagined, waiting to be discovered by a mind of unparalleled brilliance. Imagine a world grappling with superstition and arcane beliefs, where comets were seen as omens of disaster and the movements of planets were attributed to the whims of the gods. Then, into this world stepped Isaac Newton, born in the year 1642, a figure who would not only illuminate the cosmos, but also revolutionize the very way we understand reality. He wasn't just a scientist, he was a force of nature, a walking embodiment of the scientific revolution. Newton, sequestered at his family estate in Woolsthorpe during an outbreak of the plague, began to ponder the nature of gravity. The now legendary story of the apple falling from the tree may be apocryphal, embellished with time, but it captures the essence of Newton's breakthrough. What if, he wondered, the force that pulled the apple to the ground was the very same force that kept the moon in orbit around the Earth? This seemingly simple question would unlock a profound truth. The universe was not a collection of disparate phenomena, but a unified system governed by mathematical laws. His law of universal gravitation, published in 1687 in Principia Mathematica, wasn't just an equation, it was a revelation. It described a force that acted between any two objects with mass, a force that decreased with the square of the distance between them. It was elegant, it was simple, and it worked, explaining everything from the tides to the orbits of the planets with unprecedented accuracy. But what made Newton's work truly revolutionary was not just the discovery of gravity, but the demonstration that the universe was fundamentally mathematical. He showed that the language of mathematics was not just a tool for describing nature, but the very language in which nature was written. The universe, according to Newton, was a grand, predictable machine, a clockwork mechanism ticking away according to immutable laws. If you knew the initial conditions, the position and velocity of every particle, you could, in principle, predict the future with absolute certainty. This idea, known as determinism, had profound implications. It suggested that free will might be an illusion, that our actions were predetermined by the laws of physics. It challenged the religious view of a universe governed by divine intervention, replacing it with a vision of a self-regulating cosmos, operating according to rational principles. Newton's influence extended far beyond physics. His methods of calculus revolutionized mathematics, providing powerful tools for solving problems in engineering, economics, and countless other fields. His work on optics, explaining the nature of light and color, transformed our understanding of the visual world. He even dabbled in alchemy, searching for the philosopher's stone, a substance believed to turn base metals into gold, perhaps driven by that same innate desire to find a single key to unlock all the universe's secrets. Newton's clockwork universe became the dominant paradigm for centuries. It inspired a new generation of scientists and engineers, fueling the Industrial Revolution and transforming society in ways that were unimaginable before. Names like James Clerk Maxwell and Michael Faraday built upon Newton's foundations, extending his mathematical framework to understand electromagnetism, further solidifying the belief that the universe could be described by a set of elegant equations. Yet, even in the triumph of Newtonian physics, there were whispers of discontent. Some philosophers questioned the implications of determinism, while others pointed out limitations in Newton's theory. Light, for example, exhibited wave-like properties that were difficult to reconcile with his corpuscular theory. But, for the most part, the clockwork universe reigned supreme, a testament to the power of human reason and the beauty of mathematical law. A shining example of what could happen when genius, curiosity, and a falling apple align. But was this the final answer? Was the universe truly nothing more than a predictable machine? The seeds of doubt had been sown, and a revolution was brewing. A revolution that would once again shatter our understanding of reality and challenge the very foundations of Newtonian physics. The quest for a unified theory was far from over, and the stage was being set for another giant leap. A leap into the strange and wondrous world of relativity and quantum mechanics. Was Newton's clockwork universe the ultimate answer? Did a single equation truly explain it all? The universe, it turns out, had a few more surprises up its sleeve, and a young patent clerk named Albert Einstein was about to pull them out. Imagine a world where space and time are not fixed and absolute, but malleable, capable of being bent and warped by the presence of mass and energy. It sounds like science fiction, doesn't it? Yet, this is precisely the revolutionary concept that Einstein unveiled in 1915 with his general theory of relativity. Einstein, born in 1879, wasn't content with Newton's description of gravity as a force acting at a distance. He envisioned gravity not as a pull, but as a curvature of space-time, a four-dimensional fabric woven from the three dimensions of space and the one dimension of time. Picture a bowling ball placed on a stretched rubber sheet. The ball creates a dip, causing marbles rolling nearby to curve towards it. That, in essence, is Einstein's gravity. Planets orbit the sun not because they are being pulled, but because they are following the curves in space-time created by the sun's immense mass. This wasn't just a subtle tweak to Newton's theory, it was a radical departure. It meant that space and time were not passive backdrops to the universe, but active participants, influenced and shaped by the matter and energy within them. Imagine the implications for our understanding of the cosmos. It meant that light itself, though massless, could be bent by gravity, a prediction that was spectacularly confirmed during a solar eclipse in 1919. Arthur Eddington, a British astronomer, led an expedition to observe the eclipse and measured the bending of starlight around the sun, providing the first concrete evidence for Einstein's theory. The news made Einstein an overnight celebrity, transforming him from a relatively unknown scientist into a global icon. General relativity wasn't just about bending light. It also predicted the existence of black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. Initially, Einstein himself was skeptical of their existence, but now we know that black holes are ubiquitous in the universe, lurking at the centers of most galaxies, monstrous cosmic vacuum cleaners devouring everything in their path. The first image of a black hole captured by the Event Horizon Telescope in 2019 was a stunning confirmation of Einstein's theory, a visual testament to the power of his imagination and mathematical genius. But Einstein's theory wasn't just about the bizarre and exotic. It also provided a new framework for understanding the universe as a whole. It led to the development of modern cosmology, the study of the origin, evolution, and fate of the universe. Einstein's equations predicted that the universe was either expanding or contracting, a notion he initially resisted, adding a cosmological constant to his equations to force a static universe. However, observations by Edwin Hubble in the 1920s revealed that the universe was indeed expanding, leading Einstein to call the cosmological constant his biggest blunder. It turns out that this blunder might not have been so big after all, as the accelerating expansion of the universe, driven by mysterious dark energy, has revived interest in the cosmological constant. Einstein's general theory of relativity is a triumph of human intellect, a testament to the power of abstract thought and mathematical reasoning. It's a theory that has reshaped our understanding of gravity, space, time, and the universe itself. Yet even with this monumental achievement, Einstein wasn't satisfied. He spent the last decades of his life searching for an even deeper unity, a single theory that could combine gravity with electromagnetism, the force that governs light and electricity. He called it a unified field theory, a quest that ultimately proved unsuccessful. Perhaps the universe, it seemed, was even more complex and mysterious than Einstein had imagined. His geometric view of gravity remains a cornerstone of modern physics to this very day, but the universe still holds secrets, and the quest for a theory of everything continues. Where did Einstein's search for a unified field theory lead him, and why did he ultimately fall short? Was his dream of a single, elegant equation destined to remain just that? A dream? The answers, as always, lie further down the path of scientific inquiry. But even as Einstein wrestled with the fabric of space-time, another revolution was brewing, a revolution that would plunge us into a realm even more bizarre and counterintuitive than relativity itself. A realm where the very nature of reality is called into question. Are you ready to dive into the quantum enigma? Imagine a world where a single particle can be in two places at once. A world where observation itself changes the outcome of an experiment. A world where cause and effect become blurred. And the very act of knowing something influences its existence. This isn't science fiction. This is the realm of quantum mechanics, the theory that governs the microscopic world of atoms and subatomic particles. Think of it as Alice's adventures in Wonderland, but instead of falling down a rabbit hole, we're shrinking down to the size of an atom, entering a world that defies all our classical intuitions. The scale is mind-boggling. If an atom were the size of a football stadium, the nucleus at its center would be a marble. And electrons, those tiny particles zipping around the nucleus, would be specks of dust. But it's not just the size that's strange, it's the behavior of these particles that truly challenges our understanding of reality. One of the most fundamental concepts in quantum mechanics is wave-particle duality. This means that particles like electrons and photons can behave as both waves and particles depending on how we observe them. Imagine throwing a baseball at a wall. It either bounces back or breaks through, right? Now imagine throwing a wave at a wall. It spreads out, passes through multiple openings, and creates an interference pattern. Quantum particles can do both. They can act like tiny bullets or like ripples in a pond, blurring the lines between what we thought we knew about the fundamental building blocks of matter. Perhaps the most famous experiment demonstrating wave-particle duality is the double-slit experiment. In this experiment, particles are fired at a screen with two slits in it. If the particles were behaving like bullets, we would expect to see two distinct bands on the screen behind the slits. But what actually happens is that the particles create an interference pattern, as if they had passed through both slits simultaneously, like waves. This experiment has been repeated countless times with different particles, always with the same mind-bending result. And then there's the uncertainty principle, formulated by Werner Heisenberg in 1927. This principle states that we cannot know both the position and the momentum of a particle with perfect accuracy. The more accurately we know one, the less accurately we know the other. It's not just a matter of limitations in our instruments, it's a fundamental property of the universe. Imagine trying to catch a fly in a dark room. The more accurately you pinpoint its location with your flashlight, the more you disturb it, making it harder to predict its next move. The uncertainty principle is like that, but on a cosmic scale. Quantum leaps are another bizarre phenomenon of the quantum world. Electrons don't move smoothly from one energy level to another. They jump instantaneously, without ever occupying the space in between. Imagine climbing a ladder, but instead of stepping on each rung, you teleport from one rung to the next. It sounds impossible, but that's exactly what electrons do. Quantum mechanics isn't just some abstract theoretical construct. It's the foundation of much of our modern technology. Lasers, transistors, medical imaging, nuclear energy all rely on the principles of quantum mechanics. It's a theory that has transformed our world in countless ways. It successfully describes three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. But here's the rub. Quantum mechanics operates with rules that are starkly different from Einstein's relativity. While relativity excels at describing the large-scale structure of the universe, the behavior of galaxies, and the curvature of spacetime, quantum mechanics reigns supreme in the microscopic world of atoms and subatomic particles. The trouble is, these two descriptions of reality are fundamentally incompatible. Relativity paints a picture of a smooth, continuous universe, while quantum mechanics reveals a universe that is grainy, probabilistic, and uncertain. The smooth curves of space-time meet the jittery uncertainty of the quantum realm. This incompatibility poses a profound challenge to physicists. It suggests that our understanding of the universe is incomplete, that there must be a deeper theory, a theory of everything, that can reconcile relativity and quantum mechanics. But how do we bridge this gap? How do we reconcile the seemingly irreconcilable? Is there a single set of rules that governs both the large and the small? This is where the real quest begins, the search for a theory that can finally unite the two pillars of modern physics. Perhaps reality isn't as solid as we perceive it to be. Maybe it's more like a dance of probabilities, a symphony of vibrating strings, or a tapestry woven from quantum loops. Could it be that our very understanding of reality needs a quantum leap? So, we've arrived at a rather peculiar juncture. Imagine building a house, a magnificent skyscraper even, only to discover that the foundations are built on two entirely different sets of blueprints. One blueprint perfectly describes the upper floors, the plumbing, the electrical wiring. The other, equally detailed, meticulously outlines the basement, the foundation, the very bedrock upon which the building rests. But here's the catch. These blueprints are utterly incompatible. The pipes don't connect, the wiring doesn't match, and the walls, well, they just don't line up. This, in essence, is the state of modern physics. We have two incredibly successful, unbelievably precise theories, general relativity and quantum mechanics, each a triumph of human intellect, each capable of predicting phenomena with astonishing accuracy. Yet, when we try to stitch them together, to create a unified picture of the universe, the whole thing falls apart. Think of it as trying to merge two masterpieces of classical music, say a Bach fugue and a Jimi Hendrix guitar solo. Both are brilliant in their own right, but try to play them simultaneously and you end up with a cacophonous mess. That's precisely the situation we face when trying to reconcile general relativity, the theory of the very large, with quantum mechanics, the theory of the very small. General relativity, as we discussed, beautifully describes gravity as the curvature of spacetime. It's the theory that governs the motion of planets, the bending of light around massive objects, the expansion of the universe itself. Quantum mechanics, on the other hand, delves into the bizarre world of atoms and subatomic particles, where things are probabilistic, uncertain, and downright strange. It's the theory that explains the behavior of electrons, the interactions of quarks, and the very nature of matter itself. But what happens when these two theories collide, when we try to apply them to situations where both gravity and quantum effects are important? That's where the real problems begin, particularly in extreme environments like black holes and the Big Bang. Consider a black hole, that cosmic abyss where gravity reigns supreme. According to general relativity, at the very center of a black hole lies a singularity, a point of infinite density where space-time is infinitely curved. It's a point where the laws of physics as we know them break down entirely. But what does quantum mechanics have to say about this singularity? Does it smooth things out, perhaps revealing some underlying quantum structure? Or does it simply add more chaos to the already perplexing picture? The truth is, we don't know. Our current theories simply cannot handle the extreme conditions at the heart of a black hole. They offer conflicting and often nonsensical predictions. And then there's the Big Bang, the moment of creation, the event that birthed the universe as we know it. According to general relativity, the Big Bang began as a singularity, an infinitely small, infinitely dense point from which everything expanded. But again, this presents a problem for quantum mechanics. How can we apply quantum principles to a singularity? What happened in those first incredibly fleeting moments after the Big Bang, when quantum gravity effects were dominant? Our current theories are simply inadequate to answer these fundamental questions. The incompatibility of general relativity and quantum mechanics isn't just an academic curiosity, it's a profound crisis in our understanding of the universe. It tells us that our current picture is incomplete, that there must be a deeper, more fundamental theory that can reconcile these two seemingly disparate realms. It's as if we're trying to understand a complex machine with only half the instruction manual. We can make it work, to some extent, but we're missing crucial pieces of the puzzle. Think of it like this. Imagine you have two different maps of the same city. One map accurately shows the streets and buildings. The other accurately shows the subway system. Both maps are useful on their own, but if you want to navigate the entire city, you need a map that integrates both the surface and the underground. That's what we're striving for in physics. A single, unified map of the universe that can describe everything from the smallest subatomic particle to the largest galaxy. Bridging this gap, finding this theory of everything, is arguably the greatest challenge facing physicists today. It requires us to question our most basic assumptions about space, time, matter, and energy. It demands that we push the boundaries of human knowledge and creativity. Some believe the answer lies in string theory, others in loop quantum gravity. But the truth is, we're still searching, still exploring, still trying to decipher the ultimate code of the cosmos. Perhaps the solution involves concepts we haven't even imagined yet. Ideas so radical they would challenge everything we think we know about reality. This is not just a quest for equations. It's a quest for understanding. A quest to unravel the deepest mysteries of existence. It's a journey that will undoubtedly lead us down unexpected paths, challenge our assumptions, and perhaps ultimately reveal the true nature of the universe. But the road ahead is far from certain. filled with theoretical roadblocks and experimental hurdles. The question remains, can we truly bridge this divide? Can we finally find the key to unlock the universe's deepest secrets? So, we are left with this unsettling reality. The two most successful theories in the history of physics, the twin pillars upon which our understanding of the universe rests, simply refuse to play nice. It's a cosmic tug-of-war, with relativity and quantum mechanics pulling in opposite directions, threatening to tear our entire picture of reality apart. But what if I told you that amidst this apparent chaos there exists a beacon of hope, a framework that, against all odds, has managed to bring a semblance of order to the subatomic zoo? Enter the Standard Model of particle physics, a quantum framework that, in essence, is humanity's most successful attempt to date to describe all known fundamental forces and particles in the universe, with one glaring exception that we will get to a bit later. Imagine a vast, intricate tapestry woven from the threads of mathematics and experimental data, a tapestry that depicts the fundamental constituents of matter and the forces that govern their interactions. That, in a nutshell, is the Standard Model. Think of it as the periodic table of particle physics, but instead of elements, it lists all the known fundamental particles: quarks, leptons, bosons. Quarks, the building blocks of protons and neutrons, come in 6 flavors: up, down, charm, strange, top, and bottom. Leptons, the lightweight particles, include electrons, muons, taus, and their corresponding neutrinos. And then there are the bosons, the force carriers, photons for electromagnetism, gluons for the strong nuclear force, and the W and Z bosons for the weak nuclear force. These are the players, the actors on the stage of the universe. But the Standard Model is more than just a catalog of particles. It's a set of rules, a mathematical framework that dictates how these particles interact. It's based on the principles of quantum field theory, which combines quantum mechanics with special relativity. It describes how particles exchange force carrying bosons, mediating interactions like electromagnetism, which binds electrons to nuclei, the strong nuclear force, which holds quarks together inside protons and neutrons, and the weak nuclear force, which is responsible for radioactive decay. The Standard Model has been tested with incredible precision over the past few decades with experiments at particle accelerators like the Large Electron-Positron Collider at CERN and the Tevatron at Fermilab, confirming its predictions to a remarkable degree of accuracy. It predicted the existence of the W and Z bosons, which were discovered at CERN in the 1980s, and the top quark, which was discovered at Fermilab in 1995. Each discovery was a triumph for the Standard Model, a validation of its mathematical framework and its ability to describe the fundamental laws of nature. Perhaps the greatest triumph of the Standard Model came in 2012 with the discovery of the Higgs boson at the Large Hadron Collider at CERN. The Higgs boson is the particle associated with the Higgs field, a field that permeates all of space and is responsible for giving particles their mass. It's like a cosmic molasses, slowing down some particles more than others, giving them different masses. The discovery of the Higgs boson was the final piece of the puzzle, the last missing ingredient in the Standard Model. It was a moment of jubilation for physicists around the world, a culmination of decades of effort and investment. But even with all its successes, the Standard Model is not the final word. It has limitations, shortcomings that hint at a deeper, more fundamental theory. For one, it doesn't include gravity. Gravity is described by Einstein's general theory of relativity, which, as we discussed, is incompatible with quantum mechanics. The Standard Model is a quantum theory of the other 3 forces, but it has nothing to say about gravity. It's as if we have a beautiful painting that depicts all the colors of the rainbow except for one crucial shade. And then there's the mystery of dark matter and dark energy. Observations have shown that the vast majority of the universe is composed of dark matter and dark energy, substances that we cannot see or interact with using our current technology. The Standard Model does not account for dark matter or dark energy. It only describes the ordinary matter that makes up stars, planets, and us. It's like trying to understand the ocean with only a map of the coastline, ignoring the vast, unexplored depths below. Furthermore, the Standard Model leaves many questions unanswered. Why are there 3 generations of quarks and leptons? Why do particles have the masses they do? What is the nature of neutrinos? Why is there more matter than antimatter in the universe? These are fundamental questions that the Standard Model cannot answer. It's a stunning achievement, but it's clearly not the final word. It's a masterpiece, but it's an unfinished masterpiece. The Standard Model, for all its predictive power and experimental verification, is ultimately incomplete. It's a testament to human ingenuity and our ability to understand the universe at its most fundamental level, but it's also a reminder of how much we still don't know. It's a stepping stone on the path to a deeper, more complete theory, a theory that can finally unite all the forces of nature and explain the mysteries of dark matter and dark energy. Is the Standard Model just a piece of a much larger puzzle, or is it a fundamental building block upon which we can construct a truly complete picture of the universe? Only time and continued scientific inquiry will tell. The whispers of something beyond the Standard Model are growing louder, hinting at a grander, more unified picture of reality. Where do we turn next in our quest for ultimate understanding? But is the Standard Model just a temporary placeholder, a roadmap that only leads us to the edge of the map? The quest for unification, it turns out, didn't begin with string theory or loop quantum gravity. Long before the Large Hadron Collider and the Internet, physicists were already grappling with the same fundamental questions. Can we find a single theory that explains all the forces of nature? Can we unify gravity with electromagnetism, the force that lights up our cities and powers our devices? Some of the brightest minds in history dared to dream of a complete and elegant equation, a so-called unified field theory. But these early attempts, often mathematically complex and ultimately unsuccessful, were crucial stepping stones on the long and winding road to understanding the universe. Think back to the early 20th century, a time of immense scientific upheaval. Einstein had just revolutionized our understanding of gravity with his general theory of relativity. Quantum mechanics was beginning to unravel the mysteries of the atom. It was a time of great excitement and even greater uncertainty. And at the center of it all stood Albert Einstein, driven by an almost obsessive desire to find a single theory that could explain everything. Einstein wasn't alone in this pursuit. Other physicists, inspired by his success with relativity, began to explore ways to unify gravity with electromagnetism. One of the most intriguing early attempts came from a relatively unknown German mathematician and physicist named Theodor Kaluza, born in 1885. In 1921, Kaluza sent a paper to Einstein with a bold and seemingly outlandish proposal. What if, he suggested, the universe had more than the 3 spatial dimensions we perceive? What if there was a fourth, a hidden dimension, curled up so small that we couldn't see it? It sounded like science fiction, yet Kaluza showed that by adding this extra dimension to Einstein's equations of general relativity, he could derive not only the equations of gravity, but also the equations of electromagnetism. It was a stunning achievement, a mathematical tour de force that seemed to offer a glimpse of a unified theory. Einstein was initially skeptical, but after carefully reviewing Kaluza's work, he was intrigued. He eventually published Kaluza's paper, launching a flurry of research into what became known as Kaluza-Klein theory. The idea that extra dimensions could unify the forces of nature was revolutionary, and it captivated the imagination of physicists for decades. But what exactly was this hidden dimension supposed to be like? Imagine an ant walking along a tightrope. To the ant, the tightrope appears to be a one-dimensional object, a line. But to us, we can see that the tightrope also has a thickness, a second dimension that the ant is unaware of. Kaluza suggested that our universe is like the tightrope, and that there is an extra, curled-up dimension at every point in space, too small for us to detect. A Swedish physicist named Oskar Klein, born in 1894, further developed Kaluza's idea, suggesting that the extra dimension was curled up into a tiny circle with a size on the order of the Planck length, an unimaginably small distance of about 10 to the power of -35 meters. At this scale, space becomes grainy and quantized, and the laws of physics as we know them begin to break down. Klein's work helped to solidify the mathematical foundation of Kaluza-Klein theory and to make it more physically plausible. But despite its initial promise, Kaluza-Klein theory eventually ran into problems. For one thing, it predicted the existence of new particles that have never been observed. It also failed to explain the weak and strong nuclear forces which were discovered later in the 20th century. And perhaps most importantly, it didn't provide a compelling reason for why the extra dimension should be curled up into such a small size. It seemed like an ad hoc solution, a mathematical trick that didn't reflect any deeper physical reality. Over the years, other physicists attempted to build on Kaluza-Klein theory, adding more dimensions and introducing new mathematical structures. But these attempts were largely unsuccessful. The equations became increasingly complex, and the predictions became increasingly difficult to test. Eventually, Kaluza-Klein theory fell out of favor, overshadowed by the success of quantum field theory and the standard model of particle physics. Despite its limitations, Kaluza-Klein theory was a crucial stepping stone in the quest for unification. It introduced the idea of extra dimensions, which would later become a central feature of string theory. It also demonstrated the immense difficulty of the task of unifying gravity with the other forces of nature. It highlighted the fact that the universe may be far more complex and mysterious than we can imagine, and that the path to understanding it may require us to venture into uncharted mathematical territory. These early attempts, though ultimately unsuccessful, laid the groundwork for future generations of physicists to continue the search for a theory of everything. They remind us that scientific progress is not always a straight line, but a winding path filled with false starts and unexpected detours. But it is through these detours, through these early whispers of unification, that we may eventually stumble upon the ultimate answer. Einstein's own pursuit of a unified field theory, though ultimately fruitless, serves as a powerful reminder of the enduring human drive to understand the universe at its deepest level. He spent decades wrestling with equations, exploring different mathematical frameworks, always searching for that single elegant equation that could explain everything. While he never achieved his goal, his relentless pursuit inspired countless others to take up the challenge, to continue the quest for unification. These early efforts illuminate the immense difficulty of the task before us and highlight the persistent drive towards unification that motivates scientists to this day. But what would come next? Could any new ideas or even new mathematics break the logjam? The whispers of unification grow into intriguing echoes of what just might be the answer. But even as these giants of physics grappled with the complexities of the universe, a new generation of thinkers began to question the very foundations upon which our understanding was built. What if, they wondered, our fundamental assumptions about the nature of reality were wrong? What if the particles we thought were point-like, the smallest indivisible units of matter, were not point-like at all? What if instead they were something far more exotic, something far more fundamental? Imagine for a moment that you are a musician, a virtuoso guitarist perhaps. You pluck a string on your instrument and that single string vibrates, creating a beautiful, resonant tone. Now imagine that the entire universe is composed of such strings vibrating at different frequencies, creating a cosmic symphony of particles and forces. This, in essence, is the radical idea at the heart of string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny vibrating strings. These strings are so small, smaller than an atom by a factor of 100 billion, that we cannot see them even with the most powerful microscopes. It's like trying to see the individual threads of a spider web from across a football field. They are simply too small to resolve. But if these strings are so small, how can they possibly explain the diversity of particles we observe in the universe? The answer lies in their vibrations. Just like a guitar string can vibrate in different modes, creating different notes, these fundamental strings can vibrate in different patterns, each pattern corresponding to a different particle. A string vibrating in one way might appear to us as an electron, while a string vibrating in another way might appear as a quark. It's as if the universe is a giant orchestra, with each string playing a different instrument, creating a harmonious blend of particles and forces. Perhaps the most remarkable aspect of string theory is its ability to potentially unify all the forces of nature, including gravity. For decades, physicists have struggled to reconcile general relativity, which describes gravity, with quantum mechanics, which describes the other three forces. String theory offers a possible solution, a framework that can incorporate both gravity and quantum mechanics into a single, consistent theory. One of the key ingredients in string theory is the graviton, the hypothetical particle that mediates the force of gravity. In string theory, the graviton emerges naturally as one of the vibrational modes of the fundamental string. It's as if gravity is not a separate force, but simply a manifestation of the underlying stringy nature of reality. The very mathematics that underpins string theory predicts its existence without it being put in as input. Think of it this way. Imagine you are looking at a tapestry from a distance. From afar, it appears to be a continuous, smooth surface. But as you get closer, you begin to see the individual threads that make up the tapestry. String theory suggests that space-time itself, the fabric of the universe, is like that tapestry. At large scales, it appears to be smooth and continuous, as described by general relativity. But at the smallest scales, it is made up of tiny, vibrating strings, the fundamental building blocks of reality. String theory is not just a theory of particles and forces. It's a theory of space and time itself. It suggests that space-time is not a fixed, immutable background, but a dynamic, fluctuating entity that is intimately intertwined with the strings that make up the universe. It's a radical departure from our classical notions of space and time, a glimpse into a world where the very fabric of reality is woven from the threads of vibrating strings. But string theory is not without its challenges. It is a highly complex and mathematically demanding theory, and it has yet to make any testable predictions that can be verified by experiment. It is still very much a work in progress, a framework that is constantly evolving and being refined. It requires a lot of math to even understand at its core. Imagine trying to compose a symphony with an instrument you've never seen before, using a language you barely understand. That's the challenge facing string theorists today. They are exploring uncharted mathematical territory, searching for the equations that will unlock the secrets of the universe. Yet the lure of a unified theory, the promise of a single framework that can explain all the forces and particles of nature, is too compelling to resist. Could the universe really be composed of minuscule vibrating strings, a cosmic symphony of particles and forces? Is string theory the key to unlocking the ultimate secrets of reality? While experimental proof remains elusive, the allure of this mathematically elegant framework continues to captivate physicists around the globe. Is this cosmic music a mere illusion, or is it a genuine harmony of the spheres? But even if we embrace this cosmic music, this universe of vibrating strings, a perplexing question remains. We experience the world in three spatial dimensions: length, width, and height. Add time, and we have the four dimensions that Einstein wove into the fabric of space-time. But string theory, in its elegant mathematical formulation, demands something far stranger. It requires not 3, not 4, but a staggering 10 dimensions or even 11 dimensions to be true. Where are these extra dimensions? Why can't we see them? Are they hiding in plain sight, woven into the very fabric of reality just beyond our perception? Think of it as a tightly coiled garden hose. From a distance, it appears to be a one-dimensional line, but up close you see that it also has a circular dimension curled up so small that it's almost invisible. String theory suggests that the extra dimensions are like that circular dimension on the hose, curled up or compactified to incredibly small sizes, far below the resolution of our most powerful instruments. They're there, influencing the laws of physics, but we can't directly observe them. Imagine an ant walking along that garden hose. It can move forward and backward along the length of the hose, but it can also move around the circular dimension, although it may not even realize it's there. Similarly, we are confined to the three spatial dimensions we perceive, but the fundamental particles that make up our universe may be able to move in these extra, hidden dimensions. These extra dimensions aren't just mathematical abstractions. They have profound implications for the laws of physics we observe. The geometry of these hidden dimensions, their shape and size, could determine the types of particles that exist in our universe, the strengths of the forces that govern their interactions, and even the fundamental constants of nature. It's as if the extra dimensions are a hidden sculptor, shaping the universe from behind the scenes, dictating the rules of the game without us even knowing it. One way to visualize these extra dimensions is to think of a Calabi-Yau manifold, a complex six-dimensional geometric shape that string theorists often use to model the compactified dimensions. These manifolds are incredibly intricate, with countless holes and curves, and their geometry can determine the properties of the particles that emerge from string theory. Imagine a kaleidoscope, where the patterns you see depend on the shape and arrangement of the mirrors inside. The Calabi-Yau manifold is like that kaleidoscope, shaping the fundamental particles of our universe through its complex geometry. But how can we possibly test the existence of these extra dimensions? If they're too small to see, how can we ever hope to detect them? Physicists are exploring various possibilities, searching for subtle, indirect clues that might betray their presence. One idea is to look for the effects of extra dimensions on the force of gravity. Gravity, as we know it, follows an inverse square law, meaning that its strength decreases with the square of the distance. But if there are extra dimensions, gravity might leak into those dimensions at very small distances, causing the inverse square law to break down. Experiments are underway to measure the force of gravity at very short distances, searching for any deviations from the expected behavior. Another possibility is to look for new particles that might be associated with the extra dimensions. These particles, known as Kaluza-Klein modes, would be heavier versions of the particles we already know, and they might be detectable at the Large Hadron Collider or future particle accelerators. It's like searching for echoes of familiar sounds in a new, unexplored space. Consider also the possibility that these extra dimensions are not static, but dynamic, constantly changing their shape and size. This could have profound effects on the universe, potentially leading to variations in the fundamental constants of nature over time. Scientists are looking for evidence of such variations in the spectra of distant quasars, searching for subtle shifts in the wavelengths of light that might indicate a changing universe. The idea of extra dimensions is undoubtedly mind-bending, challenging our most basic intuitions about the nature of reality. It requires us to imagine a universe far more complex and mysterious than we ever thought possible. But if string theory is correct, these extra dimensions are not just a mathematical curiosity. They are an integral part of the universe, shaping the laws of physics and influencing the very fabric of space-time. Perhaps reality is not limited to what our senses can perceive, and there are hidden realms, dimensions beyond our sight, waiting to be discovered. But how far beyond our current scientific landscape will we have to journey? Are the tools to even see this landscape already in our grasp? But even as we imagine these hidden dimensions shaping our reality, a deeper puzzle emerges. What if string theory, in its initial formulation, wasn't just one theory, but a collection of related, yet distinct, perspectives on the same underlying reality? As string theory evolved, physicists found themselves facing a bewildering landscape. Not one, but 5 different, mathematically consistent versions of string theory emerged, each with its own unique properties and assumptions. It was as if they had discovered 5 different maps of the same territory, each highlighting different features and using different symbols. How could 5 different theories all be describing the same universe? Adding to the complexity, another contender entered the arena: supergravity, a theory that combines general relativity with supersymmetry, a mathematical framework that predicts a symmetry between bosons and fermions, the 2 fundamental types of particles. Supergravity offered an alternative approach to unifying gravity with the other forces, but it too had its own set of challenges. Was supergravity a competitor to string theory, or was it somehow related? The landscape of theoretical physics was becoming increasingly fragmented with no clear path forward. Then, in the mid-1990s, a breakthrough occurred, a moment of intellectual synthesis that would forever change our understanding of string theory. A brilliant physicist named Edward Witten, a professor at the Institute for Advanced Study in Princeton, proposed a radical idea: that these 5 different versions of string theory, along with supergravity, were not separate theories at all, but different facets of a single underlying framework. He called this framework M-theory, a name that remains shrouded in mystery, with Witten himself suggesting that the M could stand for membrane, matrix, or even mystery, depending on one's perspective. Imagine 5 blindfolded individuals, each examining a different part of an elephant. One feels the trunk, another the leg, another the ear, and so on. Each individual comes to a different conclusion about what an elephant is, based on their limited experience. But someone who could see the entire elephant would understand that these are all just different parts of the same animal. Witten proposed that M-theory was like that someone, offering a comprehensive view that could reconcile the seemingly disparate perspectives of the 5 different string theories. M-theory is a hypothesized framework that aims to unify these different string theories into a single, overarching structure existing in 11 dimensions. Yes, you heard that right, 11 dimensions. Just when you thought 10 dimensions was mind-bending, M-theory takes it one step further. These extra dimensions are even more mysterious than the ones proposed in string theory, and their geometry is even more complex. But what exactly are the fundamental objects in M-theory? Are they still strings? The answer, it turns out, is both yes and no. M-theory suggests that the fundamental objects might include higher dimensional membranes, often called branes, in addition to strings. Branes are like extended versions of strings. They can be 2-dimensional, 3-dimensional, or even higher dimensional objects. Imagine a sheet of paper, a 2-dimensional brane, floating in 11-dimensional space. Just as strings can vibrate, branes can also vibrate and fluctuate, and these vibrations could correspond to different particles and forces. M-theory remains a mysterious but compelling candidate for the ultimate theory. It's a framework that is still under development, a work in progress. But it offers a tantalizing glimpse of a unified picture of the universe, a picture where all the forces of nature are united, where all the particles are just different vibrations of fundamental strings and branes, and where the very fabric of spacetime is woven from the threads of 11 dimensions. But M-theory is not without its challenges. It is an incredibly complex and mathematically demanding theory, and it has yet to make any testable predictions that can be verified by experiment. It's as if we've discovered a beautiful, intricate map of a vast, unexplored territory, but we don't yet have the tools to explore that territory. Will M-theory ultimately prove to be the mother of all strings, the ultimate theory of everything? Or will it turn out to be just another false start on the long and winding road to understanding the universe? The question is whether a new breakthrough might be just around the corner, but even with this potential mother of all theories in our grasp, a cosmic conundrum arises that throws the very nature of prediction into question. Imagine you're a cartographer, charting not just one world but an infinite number of them. How do you create a map when the terrain keeps shifting, when the laws of physics themselves vary from one place to another. This is the challenge posed by the string landscape. String theory's mathematics, for all its elegance, allows for a staggering number of possible solutions. Some estimations put the figure at 10 to the power of 500, an unfathomable number so large it dwarfs the number of atoms in the observable universe. Each of these solutions describes a different universe, with potentially different physical laws, different fundamental constants, and different types of particles. It's as if the universe isn't just one place, but an infinite array of possibilities, a vast multiverse of cosmic diversity. This concept, known as the string landscape, has ignited a fierce debate among physicists. Does this undermine the theory's predictive power, rendering it essentially untestable? Or is it a glimpse into a far grander cosmic reality, a universe far more diverse and complex than we ever imagined? Think of it this way. Imagine you're trying to predict the weather, but instead of just one atmosphere to consider, you have an infinite number of them, each with its own unique conditions. How do you make a forecast? How do you determine which universe we happen to inhabit? Some physicists argue that the string landscape is a fatal flaw, that it makes string theory essentially useless as a scientific theory. If anything is possible, then nothing can be predicted, and the theory loses its ability to make testable claims. It's as if we've found a map that shows every possible route, but offers no guidance on which one to take. Others, however, see the string landscape as a potential strength, a sign that string theory is pointing us towards a deeper understanding of the universe. Perhaps our universe is just one tiny corner of a vast multiverse, a bubble of reality with its own unique set of physical laws. Maybe the constants of nature aren't fixed and immutable, but rather environmental variables determined by the specific conditions in our corner of the multiverse. Could it be that the reason our universe is so finely tuned for life, the reason the constants of nature are so precisely balanced, is simply because we happen to live in one of the few universes where life is possible? In an infinite multiverse, there would be countless universes with different values for these constants, most of which would be utterly inhospitable to life. We just happen to be in one of the lucky ones. This idea, known as the anthropic principle, is controversial, but it offers a potential explanation for the fine-tuning problem, the observation that the universe seems remarkably well suited for our existence. Perhaps the multiverse isn't a flaw in string theory, but a necessity, a consequence of the fundamental laws of physics. The philosophical implications of the string landscape and the multiverse are profound. If our universe is just one of many, does that diminish its significance? Does it mean that our existence is merely a cosmic accident, a random occurrence in an infinite sea of possibilities? Or does it perhaps suggest a deeper level of order, a grand design that encompasses the entire multiverse? The debate surrounding the string landscape is far from settled. It's a question that pushes us to the very limits of our understanding, forcing us to confront the deepest mysteries of existence. Are we on the verge of a new scientific revolution? A paradigm shift that will forever change our view of the universe? Maybe one day the tools we need to observe these other universes will appear, and maybe not. But until that day comes, we are left to ponder the possibility that our cosmos is just one of a seemingly infinite collection of realities, each governed by its own unique set of physical laws. But is there anything that would allow us to separate these theories? But amidst this quest for vibrating strings and hidden dimensions, is there another path, a road less traveled, that might lead us to the summit of quantum gravity? What if, instead of starting with particles, we began with spacetime itself? What if we took Einstein's masterpiece, general relativity, and applied the principles of quantum mechanics directly to it without any extra bells and whistles? Enter loop quantum gravity, an alternative approach that dares to challenge the very notion of a smooth, continuous space-time. Imagine that you zoom in closer and closer, past atoms, past quarks, past even the vibrating strings of string theory. What do you find? Loop. Quantum gravity proposes that you will discover that spacetime itself is not a smooth fabric, but rather a network of discrete, indivisible units, like tiny grains of sand forming a beach. It suggests that space and time are not fundamental, but emerge from something even more basic, a quantum structure woven from countless interconnected loops. Think of it as a tapestry, but instead of threads, it's woven from quantum threads of space and time. Each loop is incredibly small, on the order of the Planck length, about 10 to the power of negative 35 meters, the scale at which quantum effects of gravity become significant. These loops are interconnected, forming a network, a spin network that represents the quantum state of geometry. It is a web of relationships that define the very structure of space. But if space is quantized, what does that mean for our understanding of distance and volume? Loop quantum gravity suggests that area and volume are also quantized, taking on only discrete values like the rungs on a ladder. Imagine trying to measure the area of a square, but instead of getting a continuous value, you could only get certain specific amounts like 1 square Planck length, 2 square Planck lengths, 3 square Planck lengths, and so on. It would be as if the universe came in prepackaged chunks. This quantization of spacetime has profound implications for our understanding of gravity. It suggests that gravity is not a force acting on spacetime, but rather an intrinsic property of spacetime itself. It is a consequence of the underlying quantum structure. Einstein's smooth, curved spacetime emerges as an approximation, a large-scale average of this underlying quantum geometry. Imagine looking at a pointillist painting from a distance. From afar, it appears to be a continuous image, but up close, you see that it's made up of countless individual dots. Similarly, loop quantum gravity suggests that spacetime is like that pointillist painting, smooth and continuous at large scales, but discrete and quantized at the Planck scale. One of the key advantages of loop quantum gravity is that it is background independent. This means that it doesn't assume a pre-existing spacetime background, as string theory does. It builds spacetime from the ground up, from the quantum loops themselves. This is particularly important when dealing with extreme situations like the Big Bang, where the very notion of space-time breaks down. Imagine trying to understand the ocean without assuming a coastline. That's what loop quantum gravity is trying to do with space-time. It is trying to understand the fundamental nature of space and time without relying on any pre-existing assumptions. One of the most intriguing implications of loop quantum gravity is the possibility of a quantum foam, a frothy, fluctuating space-time at the Planck scale. At this scale, space and time would be constantly popping in and out of existence, creating a chaotic, ever-changing landscape. It would be as if the universe were boiling at its smallest scales. Moreover, what if loop quantum gravity could rewrite the story of our universe's beginning? The Big Bang presents a major challenge to our understanding, a singularity where known laws break down. But could the discrete nature of space and time in loop quantum gravity offer a resolution? Some physicists propose that instead of a Big Bang singularity, there was a big bounce, a transition from a contracting universe to an expanding one. It is a possibility that our universe is just one in a cycle of universes, expanding and contracting, bouncing from one phase to the next. Loop quantum gravity paints a fundamentally different picture of reality's fabric than string theory. It is an ambitious attempt to quantize gravity directly without relying on extra dimensions or new particles. It's a challenging path, one fraught with mathematical complexities and conceptual hurdles. But it offers a tantalizing glimpse of a universe where space and time are not continuous, but quantized, woven from a network of interconnected loops. It suggests that the very fabric of reality is granular, composed of discrete, indivisible units. But how far can this radically different approach take us? What does it really mean to weave space-time from quantum threads? But how far can this radically different approach take us? What does it really mean to weave space-time from quantum threads? Imagine, if you will, diving into the deepest ocean, further than sunlight can penetrate, where the pressure is immense and the landscape is utterly alien. At those depths, you might encounter strange and wondrous creatures, life forms that have adapted to the extreme conditions. Now, imagine diving even deeper, beyond the realm of atoms, beyond the reach of our most powerful microscopes, to a place where the very fabric of reality is being woven and unraveled. Could it be that what we perceive as empty space is, in fact, teeming with activity, a seething ocean of quantum fluctuations? Think of it as quantum foam, a chaotic froth of virtual particles popping in and out of existence, a place where the laws of physics as we know them become blurred and uncertain. It's a mind-bending concept, but it's a natural consequence of applying quantum mechanics to gravity. At the Planck scale, the smallest possible unit of length, space-time itself becomes grainy and discontinuous, like a digital image magnified to the point where you can see the individual pixels. But what does this mean for our understanding of the universe's origins? For decades, the Big Bang has been the dominant paradigm, the idea that the universe began as a singularity, an infinitely dense point from which everything expanded. However, this singularity presents a major problem for physicists. It's a place where the laws of physics break down, where our theories become meaningless. Could loop quantum gravity offer an alternative, a way to avoid the singularity altogether? Some physicists believe that it can, replacing the Big Bang with a big bounce. Imagine a universe that is not born from nothing, but rather emerges from a previous universe that was contracting. As this universe contracts, it reaches a point of maximum density, not an infinitely dense singularity, but a state where quantum gravity effects become dominant. Instead of collapsing into nothingness, the universe bounces, transitioning from a contracting phase to an expanding phase, giving birth to the universe we see today. It's a mind-boggling idea, but it's a natural consequence of the quantization of space-time. In loop quantum gravity, there is a minimum size for space and time, preventing the universe from collapsing into a singularity. It's as if there's a cosmic trampoline bouncing the universe back from the brink of oblivion. One of the key strengths of loop quantum gravity is its background independence. Unlike string theory, which relies on a pre-existing space-time background, loop quantum gravity builds space-time from the ground up, from the quantum loops themselves. This is crucial when dealing with the Big Bang, where the very notion of space-time is questionable. It's like trying to understand the construction of a house without assuming a foundation. Loop quantum gravity allows us to build the foundation itself, to understand how space-time emerges from the quantum realm. Imagine the universe as an endless cycle of expansion and contraction, a cosmic heartbeat pulsing through eternity. Each cycle begins with a big bounce, a transition from a contracting phase to an expanding phase, giving birth to a new universe. Our universe might just be one in an infinite series of universes, each with its own unique properties and laws. It is worth wondering, could this cyclic model help explain some of the mysteries of the universe, such as the origin of dark matter and dark energy? What would it mean for our understanding of time itself, if the universe had no beginning and no end? The implications of loop quantum gravity are profound, challenging our most basic assumptions about the nature of space, time, and the universe itself. It is a bold and ambitious theory, one that has the potential to revolutionize our understanding of gravity and the cosmos. From a smooth and continuous ocean to something far more tumultuous, there is much more to learn before any grand theory can be etched in stone. But the search continues, pushing the boundaries of what we know and of what we believe possible. But as we ponder the possibility of a granular spacetime, a critical question arises. If we have these two incredibly different, yet compelling frameworks for understanding the universe at its most fundamental level, How do we choose between them? String theory and loop quantum gravity, both vying for the title of theory of everything, stand as intellectual titans, each with its own strengths, weaknesses, and fiercely devoted followers. It's a scientific showdown, a battle of ideas that could reshape our understanding of reality. But how do these dueling frameworks actually compare? What are their core differences, and why is it so difficult to find experimental evidence to support either one? Think of it as a clash of artistic styles. String theory, with its elegant mathematics and reliance on extra dimensions, might be likened to a sprawling, ambitious symphony, a cosmic opera with a cast of countless characters. Loop quantum gravity, on the other hand, could be compared to a minimalist sculpture, a stark and powerful statement crafted from the very fabric of spacetime. Both are beautiful, both are profound, but they approach the problem of quantum gravity from vastly different angles. The starting points for these two theories could hardly be more dissimilar. String theory begins with the assumption that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings. From this seemingly simple assumption, it attempts to build a unified theory of all the forces and particles in nature, including gravity. Loop quantum gravity, in contrast, takes Einstein's general theory of relativity as its starting point and attempts to quantize it directly, without introducing any new particles or dimensions. It's a bottom-up approach, building spacetime from the quantum loops themselves. Their mathematical tools are equally distinct. String theory relies on sophisticated techniques from string theory, quantum field theory, and complex analysis. It's a mathematically rich and rewarding field, but it also requires a deep understanding of abstract concepts. Loop quantum gravity, on the other hand, employs techniques from general relativity, quantum mechanics, and differential geometry. It's a mathematically challenging field, but it's more grounded in the familiar concepts of space and time. Perhaps the most striking difference between these two theories lies in their assumptions about dimensions. String theory requires the existence of 10 or 11 dimensions, while loop quantum gravity makes no such assumption. Loop quantum gravity, based on observation, assumes that the universe operates on 3 spatial dimensions. However, it is not limited to this number. String theory posits that these extra dimensions are curled up or compactified at incredibly small scales, while loop quantum gravity focuses on quantizing the 3 dimensions we already observe. It's a fundamental difference in perspective, a disagreement about the very nature of reality. Moreover, their potential predictions diverge significantly. String theory predicts a whole host of new particles, including supersymmetric partners for all the known particles. These particles, if they exist, could be detected at the Large Hadron Collider or future particle accelerators. Loop quantum gravity, on the other hand, predicts subtle effects on the propagation of light and gravity, which might be detectable through astronomical observations. However, there is currently no experimental evidence to support either of these predictions. The silence from experiment is deafening. This lack of experimental evidence is a major challenge for both string theory and loop quantum gravity. It's difficult to test theories that describe phenomena at such minuscule scales or colossal energies. The energies required to probe the Planck scale, the realm where quantum gravity effects become significant, are far beyond our current reach. It's like trying to study the surface of Mars with a telescope from Earth. We can see some details, but we can't get a close-up view. The ongoing debate within the physics community is fierce and passionate. Some physicists are convinced that string theory is the only viable path towards a theory of everything, while others are equally convinced that loop quantum gravity is the way to go. There are conferences, workshops, and countless papers dedicated to these two theories, with physicists on both sides passionately defending their ideas. It's a battle of intellectual titans, a struggle to understand the deepest mysteries of the universe. But the path forward remains unclear. Without experimental evidence to guide us, it's difficult to know which theory, if either, is on the right track. Perhaps the ultimate theory will be a combination of both string theory and loop quantum gravity, a synthesis of these two seemingly disparate approaches. Or perhaps it will be something entirely different, something that we haven't even imagined yet. The quest for a theory of everything is a long and arduous journey, filled with theoretical roadblocks and experimental hurdles. But it's a journey worth taking, a quest to understand the deepest secrets of the universe. And as we continue to explore the mysteries of space, time, and quantum gravity, we can only hope that we will one day find the key that unlocks the ultimate code of reality. Are there methods that will arise that will give us answers to our questions? Imagine trying to see the smallest thing imaginable, something 100 billion times smaller than an atom, or trying to recreate the energy of the Big Bang within the confines of a laboratory. Impossible, right? Welcome to the experimental challenge, the daunting task of finding tangible evidence for theories that operate at scales and energies far beyond our current capabilities. We've built mathematical castles in the sky, elegant frameworks that promise to unlock the secrets of the universe, but how can we possibly bring them down to Earth? How can we test these theories when direct observation seems utterly out of reach? It's akin to searching for a single grain of sand on every beach on Earth, or perhaps more accurately, trying to hear a single note played on a cosmic symphony where the instruments are so faint that our ears aren't even designed to detect them. Direct observation of strings or spacetime quanta, the very building blocks of these theories, is likely impossible with current technology, and perhaps even with technologies that we can only dream of. The energies required to directly probe the Planck scale, the realm where quantum gravity reigns supreme, are simply astronomical, far exceeding anything we can achieve with our current or foreseeable particle accelerators. Think of the Large Hadron Collider, the most powerful particle accelerator ever built. It's an incredible machine, a marvel of human engineering, but even it can only reach energies far below the Planck scale. To directly observe strings, we would need an accelerator the size of the Milky Way galaxy, a feat that is, to put it mildly, impractical. Are we then to simply throw up our hands and abandon the quest for a theory of everything? Are these beautiful mathematical structures destined to remain forever beyond the realm of experimental verification? Absolutely not. Scientists are not easily deterred. When the front door is locked, they find a window. When the window is barred, they dig a tunnel. The search for a theory of everything relies on finding subtle, indirect clues, faint whispers from the universe that might betray the underlying structure of reality. It's akin to being a detective piecing together fragments of evidence to solve a complex case, or perhaps more poetically, like being an archaeologist, carefully excavating ancient ruins to uncover the secrets of a lost civilization. One approach is to look for subtle deviations from the predictions of the standard model of particle physics, the reigning champion of the subatomic world. The standard model, for all its successes, is known to be incomplete, a stepping stone on the path to a deeper theory. Physicists are constantly searching for new particles and phenomena that might point beyond the standard model, hints that could lead us towards a more fundamental understanding of nature. These particles, if they exist, could be detected at the Large Hadron Collider, potentially providing evidence for string theory or other theories beyond the standard model. Another avenue of investigation lies in the realm of cosmology, the study of the universe as a whole. The early universe, in the moments after the Big Bang, was a place of extreme energy and density, a natural laboratory where quantum gravity effects might have been significant. By studying the cosmic microwave background radiation, the afterglow of the Big Bang, scientists hope to find subtle signatures of these quantum gravity effects, faint imprints of the universe's earliest moments. Or consider the enigmatic nature of black holes. These cosmic behemoths, regions of space-time where gravity reigns supreme, represent another arena where both general relativity and quantum mechanics are crucial and clash. Black holes are not just cosmic vacuum cleaners. They are also natural testing grounds for theories of quantum gravity. The information paradox, the mystery of what happens to information that falls into a black hole, is a puzzle that a successful theory of everything must resolve. By studying black holes, both theoretically and observationally, scientists hope to gain insights into the nature of quantum gravity. Perhaps the answers will come from unexpected places, from experiments that we haven't even conceived of yet. Maybe a new generation of scientists, armed with new tools and new ideas, will stumble upon a breakthrough that will revolutionize our understanding of the universe. The quest is arduous, the challenges are immense, but the potential reward is nothing less than unlocking the deepest secrets of reality. It's an intellectual adventure, a voyage into the unknown, and the journey has only just begun. What secrets might the cosmos reveal if we continue to listen intently to even the faintest echoes? But what secrets might the cosmos reveal if we continue to listen intently to even the faintest echoes? Imagine reaching back not just millions or billions of years, but to the very dawn of time, to the first sliver of a second after the universe exploded into existence. It is an epoch when energy levels were so extreme they dwarf even the most powerful events we can observe today. Forget supernovas, black hole mergers, or gamma-ray bursts. These events barely scratch the surface of the cosmic energies that permeated the early universe. But how can we possibly study such a distant and violent time? How can we glimpse the conditions that existed when the universe was a mere infant, a fraction of a second old? The answer, remarkably, lies in the faint glow that permeates the cosmos, a relic of the Big Bang known as the cosmic microwave background radiation, or CMB. Think of it as the afterglow of creation, the faint embers of the primordial fire that birthed the universe. This cosmic microwave background radiation was first detected in 1964 by Arno Penzias and Robert Wilson, two radio astronomers working at Bell Laboratories. They were trying to calibrate a microwave antenna when they stumbled upon a persistent background noise that they couldn't explain. It was a faint, uniform signal coming from all directions in the sky. After much investigation, they realized that they had discovered the afterglow of the Big Bang, a discovery that would earn them the Nobel Prize in Physics. The cosmic microwave background radiation is not just a uniform glow, it also contains tiny temperature fluctuations, minute variations in the heat of the early universe. These fluctuations, though incredibly small, are crucial because they represent the seeds of all the structure we see in the universe today, from galaxies to superclusters to the very stars that light up the night sky. Imagine blowing glass. The slightest imperfection, the smallest bubble, can ultimately determine the shape of the final piece. Similarly, these tiny temperature variations acted as seeds around which matter coalesced over billions of years, eventually forming the vast cosmic web that we observe today. But how can we possibly extract information about the early universe from these faint temperature fluctuations? That's where precision cosmology comes in, a field that combines sophisticated telescopes, advanced computer simulations, and powerful statistical techniques to analyze the cosmic microwave background radiation with unprecedented accuracy. Satellites like the Cosmic Background Explorer Satellite, or COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, and the Planck satellite have mapped the cosmic microwave background radiation with ever-increasing precision, revealing a wealth of information about the early universe. These satellites are like time machines, allowing us to peer back into the past to witness the conditions that existed when the universe was just 380,000 years old. The data from these satellites has confirmed many of the predictions of the Big Bang theory, providing strong evidence for the inflationary epoch, a period of rapid expansion that occurred in the first fraction of a second after the Big Bang. Inflation is thought to have smoothed out the universe, making it remarkably uniform on large scales, and to have amplified the quantum fluctuations that seeded the formation of galaxies. But could the cosmic microwave background radiation also hold clues about a theory of everything? Could these faint temperature fluctuations contain subtle signatures of quantum gravity effects, hints of the underlying structure of spacetime? Physicists are exploring this possibility, searching for specific patterns in the cosmic microwave background radiation that might betray the existence of extra dimensions, the quantization of spacetime, or other exotic phenomena predicted by theories like string theory and loop quantum gravity. Imagine trying to decipher a message written in the stars, a code hidden within the faint glow of the early universe. It's a challenging task, but the potential reward is immense. If we can unlock the secrets hidden within the cosmic microwave background radiation, we might finally be able to glimpse the fundamental laws that govern the universe, to understand the very nature of reality. Perhaps the patterns in the early universe are not just random fluctuations, but echoes of the universe's first moments, whispers of a deeper reality waiting to be understood. It is by reaching far, far back in space and time that we can hope to see the faint glimmer of the fundamental laws that govern all there is. What else might be written in the ancient light of the cosmos, and where else might we seek answers? But what secrets might the cosmos reveal if we continue to listen intently to even the faintest echoes? Perhaps the patterns in the early universe are not just random fluctuations, but echoes of the universe's first moments, whispers of a deeper reality waiting to be understood. It is by reaching far, far back in space and time that we can hope to see the faint glimmer of the fundamental laws that govern all there is. What else might be written in the ancient light of the cosmos, and where else might we seek answers? Imagine, then, a place so extreme, so utterly warped by gravity, that space and time themselves become twisted beyond recognition. A region of absolute darkness from which nothing, not even light, can escape. I'm talking about black holes, those cosmic enigmas that represent the ultimate battleground between Einstein's theory of general relativity and the bizarre world of quantum mechanics. Are these celestial beasts merely destroyers of all that comes too close? Or are they, in fact, cosmic laboratories holding the keys to unlocking the universe's greatest secrets? Black holes arise from the death of massive stars. When a star many times more massive than our sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. The star collapses inwards, crushing itself into an infinitesimally small point known as a singularity. Around this singularity lies the event horizon, a boundary beyond which escape is impossible. Cross it, and you are forever trapped, pulled inexorably towards the black hole's center. It's a cosmic point of no return. According to general relativity, black holes are incredibly simple objects. They are characterized by just three properties: mass electric charge and angular momentum or spin. Everything else about the star that formed the black hole, its chemical composition, its shape, its history, all of that is lost forever. The black hole becomes a smooth, featureless sphere, a cosmic information shredder. This simplicity, however, creates a problem, a paradox that has stumped physicists for decades. Consider what happens when an object falls into a black hole. According to quantum mechanics, information cannot be destroyed. It might be scrambled or encoded, but it must always be preserved. But if black holes are truly featureless, as general relativity suggests, then where does the information go? Does it disappear forever, violating a fundamental law of physics? This is the information paradox, one of the most perplexing puzzles in modern physics. One potential resolution to the information paradox lies in a phenomenon known as Hawking radiation, named after the brilliant British physicist Stephen Hawking. In the 1970s, Hawking made a groundbreaking discovery that black holes are not entirely black. Quantum mechanics allows black holes to radiate energy and slowly evaporate over vast timescales. He proved that although nothing can escape from within the event horizon, quantum effects near the horizon allow particles to be emitted. Hawking showed that near the event horizon of a black hole, virtual particle pairs can spontaneously pop into existence. These pairs consist of a particle and its antiparticle. Usually they quickly annihilate each other, but near a black hole something extraordinary can happen. If one particle falls into the black hole, the other particle can escape. This escaping particle carries away energy from the black hole, causing it to slowly shrink. But what happens to the information about the particles that fell into the black hole? Hawking initially argued that the radiation emitted by black holes is completely random thermal radiation containing no information about the black hole's interior. This would mean that information is indeed lost, violating the laws of quantum mechanics. This claim ignited a firestorm of debate among physicists, a debate that continues to this day. However, subsequent research has shown that Hawking radiation may not be entirely random. Subtle quantum effects could encode information about the black hole's interior into the radiation, allowing the information to escape as the black hole evaporates. This is a highly complex and controversial idea, but it offers a potential way to resolve the information paradox. Imagine the black hole as a cosmic hard drive slowly leaking its secrets in a highly encrypted form. Deciphering that code might allow us to understand what happens to information inside a black hole and perhaps to understand the very nature of quantum gravity. Black holes, then, are not just destroyers but also potential messengers carrying vital clues about the universe's deepest laws. The information paradox and Hawking radiation are not mere theoretical curiosities, they are powerful probes into the heart of quantum gravity. By studying these phenomena, physicists hope to develop a theory of everything that can reconcile general relativity and quantum mechanics. Perhaps the ultimate answer will be found in the holographic principle, the mind-bending idea that the information about a three-dimensional volume of space can be encoded on a two-dimensional surface much like a hologram. The holographic principle suggests that the entire universe could be a hologram projected from a distant surface, implying that our three-dimensional reality is an illusion. Imagine a future where we can create miniature black holes in the laboratory, controlling their properties and studying their radiation with unprecedented precision. What might we learn? Could we unlock new forms of energy, discover new states of matter, or even find a way to travel through wormholes, those hypothetical tunnels through space-time that connect distant regions of the universe? What awaits us as we continue to explore the mysteries of these cosmic laboratories? Perhaps we'll find that black holes are not the end of the road, but rather gateways to new dimensions or portals to other universes. Could it be that the very equations that describe these dark behemoths will reveal even more secrets about gravity and the underlying nature of our universe? The quest goes on, and perhaps, just perhaps, the answer to everything will come from the place we least expect a black hole. But what awaits us as we continue to explore the mysteries of these cosmic laboratories? What new tools will be forged to continue unlocking the secrets of the universe? Imagine then a machine so powerful, so intricate, that it makes even the most advanced microscopes look like child's toys. A device designed not to observe the universe from afar, but to recreate its most energetic moments in a controlled environment. A veritable Big Bang in a box. This is the Large Hadron Collider, the LHC, the world's most powerful particle accelerator. Buried 100 meters beneath the Franco-Swiss border near Geneva, Switzerland, this behemoth of scientific engineering stretches for 27 kilometers in circumference. It is a testament to human ingenuity, a symbol of our relentless quest to understand the fundamental laws of nature. Think of it as a 27-kilometer racetrack for subatomic particles, a place where protons are accelerated to nearly the speed of light and then smashed together in a controlled collision. Why go to such lengths, such expense, to smash tiny particles together? The answer lies in the famous equation formulated by Albert Einstein. Energy equals mass times the speed of light squared. This equation tells us that energy and mass are interchangeable, that energy can be converted into mass and vice versa. When we smash protons together at incredibly high energies, we are essentially converting that energy into new particles, particles that might not otherwise exist in our universe. It's like shaking a piggy bank really, really hard, hoping that some new coins will pop out. The LHC is designed to search for these new particles and phenomena, to push the boundaries of the standard model of particle physics, and to explore the uncharted territory beyond. It's a hunt for evidence of supersymmetry, a key ingredient in many string theories, and for signs of extra dimensions, those hidden realms that might hold the key to unifying gravity with the other forces of nature. It's a search for the missing pieces of the puzzle, the elements that will complete our understanding of the universe. One of the primary goals of the LHC is to search for evidence of supersymmetry. Supersymmetry, or SUSY, is a theoretical framework that proposes a symmetry between bosons and fermions, the two fundamental types of particles. For every known particle, supersymmetry predicts the existence of a partner particle, a superpartner, with different spin. These superpartners have never been observed, but if they exist, they could solve some of the mysteries of the standard model, such as the hierarchy problem, the question of why the Higgs boson is so much lighter than the Planck mass. Think of it as a cosmic dance where every particle has a partner mirroring its movements but with a different rhythm. The LHC also searches for signs of extra dimensions. As we discussed earlier, string theory requires the existence of 10 or 11 dimensions, while we only perceive 3 spatial dimensions and 1 time dimension. If these extra dimensions exist, they must be curled up or compactified at incredibly small scales. But even though they are hidden from our direct view, they might have subtle effects on the behavior of particles at the LHC. One possibility is that the extra dimensions could manifest themselves as new particles, known as Kaluza-Klein modes, which would be heavier versions of the particles we already know. These particles could be detected at the LHC, providing evidence for the existence of extra dimensions. The LHC is not just a machine. It's a collaboration, a global effort involving thousands of scientists from hundreds of institutions around the world. Physicists, engineers, computer scientists, all working together to design, build, and operate this complex instrument. It's a testament to the power of human collaboration, a reminder that the pursuit of knowledge transcends national borders and cultural differences. Think about that. Thousands of brilliant minds from every corner of the globe united by a single goal, understanding the secrets of the universe. The data produced by the LHC is staggering. Petabytes of information generated every second. Analyzing this data requires vast computing resources and sophisticated algorithms. The worldwide LHC computing grid, a global network of computer centers, processes and distributes this data to scientists around the world. While the LHC has made many important discoveries, including the Higgs boson, it has yet to find definitive evidence for supersymmetry or extra dimensions. But the search continues. The LHC has been upgraded, increasing its energy and luminosity, the rate at which particles collide. With these upgrades, the LHC will be able to probe even deeper into the subatomic world, potentially uncovering new particles and phenomena that could revolutionize our understanding of the universe. What new insights lie just beyond the LHC's current reach, and what other phenomena remain hidden in the dark corners of the cosmos? Imagine searching for a faint signal amidst a cacophony of noise. That's the challenge facing physicists at the LHC. But with perseverance, ingenuity, and a little bit of luck, they might just stumble upon the next great breakthrough, the discovery that will finally lead us to a theory of everything. But can our most sophisticated machines even detect these elusive particles and hidden dimensions? What if, despite all our efforts, we are only seeing a fraction of the cosmic picture? What if the universe holds secrets far more profound and perplexing than we ever imagined? Consider this. Everything we can see, everything we can touch, everything we know about the universe, from the smallest atom to the largest galaxy, accounts for only around 5% of its total mass and energy. Just 5%. What about the other 95%? Where is it, and what is it made of? This is the mystery of dark matter and dark energy, the dark side of the universe, the silent majority that shapes the cosmos from behind the scenes. Think of it as an iceberg. What we see above the water, the tip of the iceberg, represents the ordinary matter that makes up stars, planets, and us. But the vast majority of the iceberg, the part hidden beneath the surface, represents the dark matter and dark energy that we cannot see. These mysterious substances do not interact with light, making them invisible to our telescopes. They do not emit, absorb, or reflect electromagnetic radiation. They are truly dark, shrouded in mystery. But if we cannot see dark matter and dark energy, how do we know they exist? The answer lies in their gravitational effects. We can infer the presence of dark matter by observing its gravitational influence on visible matter. Galaxies, for example, rotate much faster than they should based on the amount of visible matter they contain. The stars at the edges of galaxies are moving so fast that they should be flung out into space, but they are held in place by the gravity of something we cannot see, dark matter. It's as if the galaxies are surrounded by a halo of invisible mass, a ghostly presence that keeps them from flying apart. Dark energy, on the other hand, is even more mysterious. It is a hypothetical form of energy that permeates all of space and is responsible for the accelerating expansion of the universe. In 1998, two teams of astronomers led by Saul Perlmutter, Brian Schmidt, and Adam Rees made a groundbreaking discovery. They were studying distant supernovas, exploding stars, to measure the expansion rate of the universe. To their surprise, they found that the supernovas were farther away than expected, indicating that the expansion of the universe was not slowing down, as previously thought, but accelerating. This discovery was a shock to the scientific community. It implied the existence of a mysterious force, dark energy, that was pushing the universe apart, counteracting the force of gravity. It's as if the universe is being inflated like a balloon, driven by a force we cannot see or understand. The nature of dark energy is one of the biggest mysteries in cosmology today. What is it, and where does it come from? One possibility is that dark energy is a form of vacuum energy, the energy of empty space. According to quantum mechanics, even empty space is not truly empty. It is filled with virtual particles that pop in and out of existence, creating a sea of quantum fluctuations. This vacuum energy could exert a repulsive force, driving the accelerated expansion of the universe. Another possibility is that dark energy is a new type of field, similar to the Higgs field that permeates all of space. This field, known as quintessence, would have a negative pressure, causing it to push the universe apart. The origin of dark matter and dark energy remains one of the greatest challenges facing physicists today. These mysterious substances make up 95% of the universe, yet we know almost nothing about them. Does a theory of everything hold the key to unlocking the secrets of the dark side? Could a unified theory naturally explain the nature and origin of dark matter and dark energy, solving the riddle of the universe's silent majority? Perhaps string theory, with its extra dimensions and vast landscape of possible universes, could provide a framework for understanding dark matter and dark energy. Maybe dark matter particles are hidden in the extra dimensions, or perhaps dark energy is a consequence of the geometry of the multiverse. Or could loop quantum gravity, with its quantization of space-time, offer a different perspective? Perhaps dark matter and dark energy are related to the quantum structure of space-time, emerging from the quantum foam at the Planck scale. Perhaps the answer lies in a completely new theory, something that we haven't even imagined yet. The quest to understand dark matter and dark energy is a journey into the unknown, a voyage to the very edge of our knowledge. It's a reminder that there is still so much we don't know about the universe, that the mysteries of the cosmos far outweigh our current understanding. But as we continue to explore the dark side, to probe the secrets of dark matter and dark energy, we can only hope that we will one day shed light on the universe's greatest enigmas. What if the answer to the darkness is not to find light, but to understand darkness itself? Where do we look now? Where do we look now? But what if the answer to the darkness is not to find light, but to understand darkness itself? Now consider a question that has haunted scientists and philosophers alike for centuries. Is the universe, in some fundamental way, rigged? Are the very laws of nature, the constants that govern reality, set in such a way that life as we know it was not just possible, but perhaps inevitable? Or are we simply incredibly lucky cosmic lottery winners, existing in a universe where the odds were stacked impossibly in our favor? It is one of the greatest questions ever asked, and one that even now has no answer and maybe never will. This is the realm of the fine-tuning problem, a concept that delves into the seemingly exquisite precision with which the fundamental constants of nature are calibrated. These constants, numbers like the gravitational constant, the speed of light, the mass of the electron, are the bedrock upon which our universe is built. Change them even slightly, and the cosmos as we know it would cease to exist. Stars would not form, galaxies would fall apart, and life, as we understand it, would be impossible. Imagine a radio dial. There are an infinite number of frequencies that can be selected, but only a tiny sliver is set to the radio station. Imagine a universe where the strength of gravity was even slightly stronger. Stars would burn too quickly, collapsing into black holes before life could evolve on any orbiting planets. Conversely, if gravity was even a touch weaker, stars would never ignite, unable to fuse hydrogen into helium, leaving the universe a cold, dark, and barren place. It is all so delicate, all so precise. The same holds true for the electromagnetic force, the force that binds atoms together. If it were even a fraction stronger, all stars would be red dwarfs too small and dim to support life-bearing planets. We are talking tiny degrees of change, almost impossibly sensitive. Reduce it slightly, and there would only be blue giants, short-lived behemoths, that would burn out before planets had a chance to form. Then there's the strong nuclear force, the force that holds the nuclei of atoms together. If it were just a few percent weaker, atoms themselves would be unstable matter itself, would dissolve with all known forms of life being impossible. If it were a little stronger, then all the hydrogen in the early universe would have fused into helium, leaving nothing to form water, the very source of all known life. These are not just minor adjustments we're talking about. These are incredibly precise values. The gravitational constant, for example, is fine-tuned to 1 part in 10 to the 60th power. That's a 1 followed by 60 zeros. That is like firing a bullet across the entire observable universe and hitting a 1-inch target. This remarkable precision has led some scientists and philosophers to wonder if there is something more at play. Is there a deeper principle at work, some underlying mechanism that explains why the constants of nature are so exquisitely tuned for life? One possible explanation is the multiverse. String theory, as we have discussed, predicts the existence of a vast landscape of possible universes, each with its own set of physical laws and fundamental constants. In this multiverse, the constants of nature are not fixed, but rather are environmental variables determined by the specific conditions in each universe. Most of these universes would be utterly inhospitable to life, but in a few rare cases like ours, the constants would be just right. Think of it as a cosmic Darwinism, a survival of the fittest universes. But here is the sticking point. If this explanation is true, then our existence is simply a matter of chance. We just happen to live in one of the few universes where life is possible. And you may ask, how can we claim to have solved the mysteries of the universe if the final solution is a cosmic accident? Another possibility is that there is a deeper law of nature, that we have not yet discovered a theory of everything that dictates the values of the fundamental constants. This theory would not just describe the universe, but would explain why it is the way it is. Perhaps the constants are not arbitrary at all, but are determined by some underlying mathematical principle. Perhaps somewhere out there there's the answer to the ultimate equation, and it all makes sense. But if the constants of nature are fine-tuned, then how can they be changed? Is it all chance, or is there a greater design? The fine-tuning problem raises profound questions about our place in the cosmos. Are we alone in the universe, or are there countless other life-bearing worlds? Is our existence a cosmic fluke, or is it part of some grand design? These are questions that science alone cannot answer. They delve into the realm of philosophy and metaphysics, forcing us to confront the deepest mysteries of existence. Is it a sign that the universe was created by an intelligent designer, a cosmic watchmaker who carefully set the constants of nature to allow for life? Or is it simply a reflection of the vastness and complexity of the multiverse, where anything that can happen will happen somewhere? And does this imply the existence of some higher power? Perhaps the universe is not fine-tuned at all. Perhaps our understanding of physics is incomplete, and there are other factors at play that we have not yet considered. Maybe what appears to be fine-tuning is simply a consequence of our limited knowledge, a reflection of our ignorance. It is possible that we may never know the ultimate answer, that the mysteries of the universe will always remain beyond our grasp. Is the universe a grand design or a cosmic accident? What if our entire view of the cosmos needs to be revisited? Is it not an act of supreme hubris to think that we are so close to solving the puzzle of the universe when it continues to hold us in its thrall? While string theory, loop, quantum gravity, and all the other brilliant work continues, does the problem even lie with the physics? There is much to consider and perhaps more to learn. But as we consider these questions of cosmic fine-tuning and potential multiverses, a provocative phrase often surfaces in discussions about the theory of everything, the God equation. It's a term that ignites imaginations, sparks debate, and invites both reverence and skepticism. But what do physicists really mean when they talk about the God equation? Is it a literal formula, a set of symbols that somehow reveals the mind of a creator, or is it something else entirely? The truth is, the God equation is more of a metaphor than a concrete equation. It's shorthand for the ultimate elegance, simplicity, and explanatory power that a final theory of everything would possess. Imagine a single equation, a concise, elegant statement that encapsulates all the fundamental laws of physics, explaining every force, every particle, every interaction in the universe. It would be a masterpiece of intellectual achievement, a culmination of centuries of scientific inquiry. This is what physicists are alluding to when they speak of the God equation. It's not about proving or disproving the existence of a deity, but more about encapsulating the universe in its entirety. Think of it as the ultimate haiku, a 17-syllable poem that captures the essence of existence, or a single brushstroke that perfectly embodies the beauty of a landscape. It is an aspiration for ultimate simplicity, a desire to distill the complexity of the cosmos down to its most essential form. The equation itself might not be divinely inspired, but its perfection and all-encompassing nature evokes the feeling of one. The search for the God equation isn't just about finding a formula. It's about understanding the underlying principles that govern reality. It's the intersection of science, philosophy, and the profound questions about existence that lie at the heart of this quest. The equation can almost be viewed as a guide to the cosmos or a Rosetta Stone allowing anyone to read into existence. Is it a delusion of grandeur to assume a single equation could hold all of life's answers, or is it rather an exercise in reaching for an ideal? It's a journey that takes us beyond the realm of physics into the realm of metaphysics. What does it mean to understand the universe? Can we ever truly grasp the ultimate nature of reality, or are there limits to human knowledge? These are questions that have occupied philosophers for millennia, and they are now being addressed by scientists with the tools of mathematics and experimentation. The pursuit is a reflection of humanity's deepest longings. We yearn for order in a chaotic world, meaning in a seemingly random universe, and purpose in a life that often feels fleeting. The search for the God equation is an attempt to find those things, to discover the hidden connections that bind us all together. It's a question that has been asked in different forms across cultures. From the ancient Greeks, searching for the first cause, to modern physicists seeking a unified theory, the impulse to comprehend the totality of existence remains a core human drive. What is the difference between this quest and that of theologians searching for the divine source of all things? And ultimately, can such different paths ever lead to the same destination? The God equation is a symbol of our hope for a deeper understanding, our belief that the universe is ultimately knowable, and our conviction that through reason and inquiry we can unlock its secrets. So the phrase invites many questions more than it answers, and one cannot help but ponder whether we'll ever be satisfied with the final results. But what if the universe is so complex that no single equation can ever fully capture its essence? Perhaps the beauty lies not in finding a final answer, but in the ongoing quest to understand it. But perhaps the universe is so complex that no single equation can ever fully capture its essence. Perhaps the beauty lies not in finding a final answer, but in the ongoing quest to understand it. But what if the very act of seeking this ultimate knowledge is itself constrained? What if there are inherent boundaries to what we, as humans, can comprehend about the universe? Can we ever truly know if a final, verifiable theory of everything is even attainable? Consider for a moment the realm of mathematics itself, a world of pure logic and abstract thought. Even within this seemingly perfect system, there exist limitations, boundaries beyond which our understanding cannot penetrate. Think of Kurt Gödel, the Austrian-American logician and mathematician who in 1931, at the age of just 25, shook the foundations of mathematics with his incompleteness theorems. Gödel demonstrated that within any sufficiently complex formal system, such as mathematics, there will always be statements that are true but cannot be proven within that system. It's a mind-bending concept, suggesting that there are truths that are forever beyond our reach, knowledge that is forever inaccessible. Think of it like trying to build a tower out of Lego bricks. No matter how high you build the tower, there will always be more bricks available, more combinations possible. Gödel showed that within mathematics there will always be more truths to discover, more problems to solve. But more than this, he proved that there will always be truths that you can know are true, but you can't prove are true based on the rules that you are using. It's as if there are hidden chambers within the tower that you can never reach, no matter how high you climb. Could this incompleteness extend to our understanding of the universe as a whole? Could there be fundamental laws of nature that are true but cannot be proven or even understood by human minds? It's a humbling thought, suggesting that our quest for a theory of everything may be destined to fall short, that we may never fully grasp the ultimate nature of reality. Imagine trying to assemble a jigsaw puzzle, but you are missing some of the pieces. No matter how hard you try, no matter how cleverly you arrange the remaining pieces, you will never be able to complete the puzzle. Similarly, there may be aspects of the universe that are forever hidden from our view, knowledge that is forever beyond our grasp. Or perhaps the problem lies not with the universe itself, but with our own limited cognitive abilities. The human brain, for all its remarkable capabilities, is a product of evolution, shaped by the demands of survival. It is designed to understand the world around us, to navigate our environment, and to solve practical problems. But is it capable of understanding the ultimate nature of reality? Imagine trying to teach calculus to a dog. The dog may be intelligent, but its brain is simply not equipped to grasp the abstract concepts of mathematics. Similarly, the human brain may be limited in its ability to understand the universe, to comprehend the intricacies of quantum gravity or the nature of consciousness. Consider the vastness and complexity of the cosmos. The universe is filled with billions of galaxies, each containing billions of stars. It extends for billions of light years in every direction, and it has existed for billions of years. How can we, as finite beings with limited lifespans, possibly hope to comprehend such a vast and complex system? It's like trying to map the entire ocean with a single drop of water. We can learn something about the ocean from that single drop, but we will never be able to fully grasp its immensity. Or perhaps the issue isn't only about cognitive limits, but about whether we can experimentally confirm the ultimate theory. How could you prove the existence of other universes in a multiverse if those universes are, by definition, causally disconnected from ours? How can we be sure we haven't missed something essential if it's impossible to carry out any experiment to find it? Could it be that the ultimate nature of reality is simply beyond our capacity to fully grasp or experimentally confirm? That the quest will continue, but success is destined to forever elude us? Are we in fact chasing a mirage, a beautiful but ultimately unattainable goal? There are no answers, only more questions, and that in itself may be the whole point. For it's not just about getting to the answer, but the journey we take while trying to get there. But could it be that the act of seeking this knowledge is itself restrained by limitations? That, in fact, all that exists and could exist may be beyond us? Or what is the human element in this cosmic chase? Because the quest for a theory of everything, while seemingly detached in its complex equations, is inherently a human story, a tale not just of scientific endeavor, but of personal struggles, rivalries, collaborations, and the relentless human spirit pushing against the boundaries of the unknown. Consider for a moment that science is not just a cold, objective pursuit of truth, but a vibrant tapestry woven with the threads of human emotion, ambition, and sheer, unadulterated curiosity. It is a human endeavor, and behind every breakthrough, every equation, every scientific revolution, there are individuals driven by passion, fueled by frustration, and united by a shared desire to unravel the mysteries of the universe. Think of the collaborative spirit, the moments of shared insight, the eureka moments that occur not in isolation, but through the exchange of ideas, the challenging of assumptions, and the collective pursuit of knowledge. The creation of the Standard Model, for instance, was not the work of a single genius, but the culmination of decades of research by hundreds of physicists from around the world, each contributing their piece to the puzzle. It was a symphony of intellect, a testament to the power of human collaboration. But collaboration is just one facet of the human story in science. There is also rivalry, the fierce competition between individuals and groups vying to be the first to make a groundbreaking discovery. Scientific rivalry can be intense, driving researchers to push themselves to the limits, to work tirelessly to outcompete their rivals. Remember the race to discover the structure of DNA, a saga filled with ambition, jealousy, and scientific brilliance. James Watson and Francis Crick ultimately triumphed, but their victory was built upon the work of Rosalind Franklin, whose contributions were initially overlooked. And then there is the element of perseverance, the ability to keep going in the face of setbacks, to remain dedicated to a cause despite years of fruitless effort. The search for a theory of everything is a marathon, not a sprint, and it requires a level of dedication and resilience that is truly remarkable. Think of Albert Einstein spending the last decades of his life searching for a unified field theory, a quest that ultimately proved unsuccessful. Yet his unwavering commitment to his vision inspired countless others to take up the challenge, to continue the search for unification. But who were these brilliant minds who have dedicated their lives to the search for unification? Names like Murray Gell-Mann, the American physicist who proposed the quark model, revolutionizing our understanding of the building blocks of matter. Abdus Salam, the Pakistani theoretical physicist who shared the Nobel Prize for his work on the electroweak unification, uniting the electromagnetic and weak forces. Sheldon Glashow, Steven Weinberg, all who pushed the boundaries of known physics. These individuals were not just scientific giants, they were also human beings with their own quirks, passions, and personal struggles. Did you know that Richard Feynman, the brilliant American physicist known for his work on quantum electrodynamics, was also a skilled bongo player and a notorious prankster? He even cracked safes as a hobby. Or that Paul Dirac, one of the founders of quantum mechanics, was known for his extreme reticence, often communicating in monosyllables. The personal struggles behind abstract equations are often overlooked, yet it is important to remember that these scientists faced their share of challenges, both personal and professional. The struggle to secure funding, the pressure to publish, the constant scrutiny from peers, These are all part of the scientific life. It is a challenging path, and for every victory there are countless setbacks. What of their frustrations? Think of the countless hours spent wrestling with complex equations, the dead ends, the false starts, the moments of doubt and despair. The scientific life is not always glamorous. It's often a lonely and frustrating pursuit, a constant battle against the limits of human knowledge. It's a journey that demands not just intelligence, but also resilience, determination, and a healthy dose of self-belief. But through it all, there is the unwavering pursuit of knowledge, the relentless desire to understand the universe at its deepest level. It's the intellectual thrill of discovery, the satisfaction of unraveling a complex puzzle, the sheer joy of understanding something new. It is what fuels these brilliant minds, and it is what drives them to keep pushing the boundaries of human knowledge. Their stories remind us that science is not just an accumulation of facts, but a deeply human endeavor. And what will become of these stories as the quest continues? What other individuals will rise in the face of overwhelming possibility and impossibility? But through it all, there is the unwavering pursuit of knowledge, the relentless desire to understand the universe at its deepest level. It's the intellectual thrill of discovery, the satisfaction of unraveling a complex puzzle, the sheer joy of understanding something new. It is what fuels these brilliant minds, and it is what drives them to keep pushing the boundaries of human knowledge. Their stories remind us that science is not just an accumulation of facts, but a deeply human endeavor. And what will become of these stories as the quest continues? What other individuals will rise in the face of overwhelming possibility and impossibility? What if the next breakthrough doesn't come from a seasoned professor with decades of experience, but from a bright-eyed graduate student armed with a revolutionary new idea? Or perhaps from an artificial intelligence, an algorithm capable of sifting through mountains of data and spotting patterns that no human could ever detect? The future of the search for a theory of everything is not just about new experiments and new telescopes. It's about new ways of thinking, new tools, and a willingness to challenge the very foundations upon which our understanding is built. Picture this: a new generation of colliders, far more powerful than the Large Hadron Collider, capable of reaching energies closer to the Planck scale. These machines, still decades away from realization, would be the ultimate probes of the subatomic world, allowing us to directly create and study the particles and forces that govern the universe at its most fundamental level. Imagine the discoveries that await us: supersymmetric particles, extra dimensions, perhaps even hints of the quantum nature of spacetime itself. But these next-generation colliders won't just be bigger and more powerful versions of the machines we have today. They will also be smarter, incorporating artificial intelligence to analyze data in real time, to identify patterns and anomalies that might otherwise be missed. Imagine an artificial intelligence working side by side with physicists, sifting through the trillions of events produced by the collider, searching for that one needle in a haystack that could revolutionize our understanding of the universe. And it's not just about particle physics. The future of the search also lies in the realm of gravitational wave astronomy, a new window on the universe that has only recently opened. Think back to 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, made its first historic detection of gravitational waves, ripples in spacetime caused by the collision of two black holes 1.3 billion light-years away. It was a watershed moment in science, confirming a prediction made by Albert Einstein over 100 years earlier, and ushering in a new era of astronomy. Now imagine a network of gravitational wave detectors spread across the globe, listening for the faint whispers of colliding black holes, merging neutron stars, and perhaps even the echoes of the Big Bang itself. What might we learn from these gravitational waves? Perhaps they could reveal the secrets of dark matter, the nature of dark energy, or even the existence of extra dimensions. What if, by studying the gravitational waves emitted by black holes, We could test the predictions of quantum gravity. Could we detect subtle quantum effects near the event horizon, faint echoes of the universe's most enigmatic objects? Gravitational wave astronomy is still in its infancy, but it holds tremendous potential to revolutionize our understanding of the universe. Then there is precision cosmology, the quest to measure the properties of the universe with ever-increasing accuracy. Satellites like the James Webb Space Telescope are providing us with unprecedented views of the early universe, allowing us to study the formation of the first galaxies and to probe the cosmic microwave background radiation with greater precision than ever before. By studying the cosmic microwave background radiation, we can learn about the conditions that existed in the early universe, the seeds that gave rise to the galaxies and stars we see today. We can measure the curvature of space-time, the density of matter and energy, and the expansion rate of the universe. It's a celestial treasure map that, if we listen closely, may reveal the secrets of a theory of everything. But the future of the search is not just about new experiments and new observations. It's also about new theoretical frameworks, new ways of thinking about the universe. Artificial intelligence may play a crucial role not just in analyzing data, but in formulating new theories. Imagine an artificial intelligence that is not just a tool for physicists, but a collaborator, capable of generating new mathematical models and testing them against experimental data. What if an artificial intelligence could discover a new mathematical structure, a new way of describing the universe that no human had ever conceived of? It sounds like science fiction, but it may not be as far-fetched as it seems. Artificial intelligence is already transforming many areas of science, and it is only a matter of time before it begins to play a significant role in theoretical physics. Could it be that the key to unlocking the secrets of the universe lies not in finding new particles or new dimensions, but in developing entirely new theoretical frameworks? Perhaps we need to move beyond string theory and loop quantum gravity to explore uncharted mathematical territory, to develop new concepts that challenge our most basic assumptions about the nature of reality. Perhaps the final theory will be so radical, so unexpected, that it will require a completely new language, a new way of thinking about space, time, matter, and energy. Maybe the future holds a new synthesis of ideas, a fusion of physics, mathematics, and computer science that will revolutionize our understanding of the universe. What new breakthroughs may rise in the field of quantum computing? If reality itself emerges from computation, then what could we learn from a machine built on quantum mechanical principles? The truth is, no one knows what the future holds, but one thing is certain. The quest for a theory of everything will continue to push the boundaries of human knowledge and ingenuity. But imagine for a moment that we do succeed, that we finally crack the code, that we discover the elusive theory of everything. What then? Would it simply be a triumph for physics, a cause for celebration within the scientific community? Or would it have far-reaching implications, transforming our understanding of reality, our place in the cosmos, and even the very fabric of our society? What if, by finding this ultimate equation, we are simultaneously rewriting the human story? One thing is certain: the discovery of a theory of everything would have a profound impact on our understanding of reality. It would provide us with a complete and consistent picture of the universe, from the smallest subatomic particle to the largest galaxy. We would finally understand how all the forces of nature are connected, how space and time are interwoven, and how the universe came to be. It would be as if we had suddenly gained access to the master blueprint revealing the inner workings of the cosmos. But the implications would extend far beyond the realm of physics. A theory of everything would undoubtedly revolutionize our understanding of philosophy, challenging our most basic assumptions about existence, consciousness, and the nature of reality. What would it mean for our understanding of free will if the universe is ultimately governed by deterministic laws? Would it challenge our notions of morality and ethics, forcing us to rethink our place in the grand scheme of things? Imagine the impact on our understanding of consciousness. Could a theory of everything shed light on the nature of the mind, explaining how consciousness arises from the complex interactions of matter and energy? Could it help us to understand the relationship between the brain and the soul, or perhaps even pave the way for the creation of artificial consciousness? And what of future technologies? It's difficult to even imagine the kinds of technological breakthroughs that could arise from such profound knowledge. If we truly understood the fundamental laws of nature, we could potentially manipulate matter and energy in ways that are currently beyond our wildest dreams. Perhaps we could unlock new sources of energy, develop new materials with unprecedented properties, or even create technologies that can heal the human body at the molecular level. Imagine that nanotechnology could be less fiction and more fact. Perhaps we could even develop technologies that allow us to travel to distant stars or to manipulate space and time itself. The possibilities are truly limitless. Some have even speculated that a complete understanding of physics could lead to technologies that blur the line between science and magic, allowing us to perform feats that would seem impossible today. Whether that is possible may be known, but what is knowable is that it would revolutionize our very existence. But the discovery of a theory of everything would also raise profound ethical questions. With such powerful knowledge, who would decide how it should be used? How would we ensure that this knowledge is used for the benefit of all humanity, rather than for the enrichment of a few? How would we prevent it from falling into the wrong hands, from being used for destructive purposes? Imagine the power we would wield, the responsibility that would come with it. Would we be able to handle it wisely? One cannot simply ignore the social ramifications. Would it further widen the gap between the haves and have-nots, creating a world where a select few possess godlike powers while the majority are left behind? Or could it be used to create a more equitable society where everyone has access to the benefits of this newfound knowledge? What would it mean for our understanding of religion? Could a theory of everything reconcile science and faith, providing a unified framework for understanding both the natural world and the spiritual realm? Or would it further erode religious belief, challenging the very foundations of our moral and ethical systems? The discovery of a theory of everything would be a transformative event in human history, a turning point that would alter our worldview in profound ways. It would challenge our assumptions, push the boundaries of human knowledge, and perhaps ultimately reveal the face of creation itself. It would be the ultimate test of our wisdom, our compassion, and our ability to use knowledge for the betterment of humanity. If it does happen, how would we be changed? Perhaps it would lead to a new era of enlightenment, a golden age of scientific discovery, technological innovation, and philosophical exploration. Or perhaps it would lead to a new era of conflict and division, as different groups vie for control of this powerful knowledge. The outcome is uncertain, but one thing is clear. The discovery of a theory of everything would be a game changer, a moment that would forever alter the course of human history. The journey is far from over, and so, what wonders await us around the bend? But what if the answer to the darkness is not to find light, but to understand darkness itself? The potential discovery of a theory of everything raises a question that echoes through the ages. What is next? Will humanity rest on its laurels, content with having solved the ultimate puzzle? Or will this newfound knowledge simply open up new avenues of inquiry, new mysteries to explore? Imagine scaling a mountain that pierces the clouds, believing the summit to be the highest point only to discover a vast range of peaks beyond, each beckoning with its own unique challenge. The truth is, even if we were to discover a single elegant equation that describes all the fundamental forces and particles in the universe, our quest for knowledge would not be complete. There would still be countless questions to answer, mysteries to unravel, and new frontiers to explore. Think of it as unlocking a door, not to a final destination, but to an endless corridor lined with countless other doors, each leading to a new and unknown realm. One thing remains, and that is the enduring human drive to understand the universe at its deepest level. It is a drive that has propelled us forward for centuries, from the ancient Greek philosophers pondering the nature of reality to the modern-day physicists smashing particles together at the Large Hadron Collider. This drive is not simply about acquiring knowledge. It is about something deeper, something more profound. It is about our innate curiosity, our desire to make sense of the world around us, to find meaning and purpose in a universe that often seems chaotic and indifferent. It's this innate drive which positions the search for a theory of everything to be one of the grandest intellectual adventures ever undertaken. Consider the words of Carl Sagan, the famed American astronomer and science communicator, who said that somewhere something incredible is waiting to be known. This sentiment captures the essence of the scientific spirit, the unwavering belief that there are still wonders to be discovered, secrets to be revealed, and mysteries to be unraveled. Whether or not a single equation of God is ever found the journey itself, the act of questioning, exploring, and pushing the boundaries of human knowledge is what truly matters. Or consider the words of the American singer-songwriter Joni Mitchell, who wrote that we are stardust, billion-year-old carbon. It's a humbling reminder of our place in the cosmos and our shared connection to the universe. The quest for a theory of everything is not just about understanding the universe out there, it's about understanding ourselves, about discovering our origins and our destiny. The adventure itself also reveals the profound beauty of the cosmos. Perhaps the greatest benefit of the search for a theory of everything is the knowledge we gain along the way. In our quest to understand the universe, we develop new technologies, new mathematical tools, and new ways of thinking. These innovations often have unforeseen applications, transforming our society in ways that we could never have imagined. Think of the development of quantum mechanics, which not only revolutionized our understanding of the atom, but also led to the invention of lasers, transistors, and countless other technologies that we rely on today. The search also fosters a sense of collaboration and cooperation across national boundaries and cultural divides. Scientists from all over the world are working together to solve these grand challenges, sharing their knowledge, their insights, and their passion for discovery. It is a testament to the power of human collaboration, a reminder that we are all part of something bigger than ourselves. Will new doors open, leading to new questions that will in turn make way for new expeditions? What if the pursuit of a theory of everything leads us to develop new forms of consciousness, artificial or otherwise, that allows us to understand the cosmos in ways we never could before? What if the journey has no end because the cosmos has no boundaries? This in itself might be the greatest discovery of all.